Hello, and thank you for joining us for the 49th Annual AAKP National Patient Meeting. I'm Diana Clynes, and I'm the Executive Director of the AAKP, the oldest and largest independent kidney patient organization in the nation. It's my honor to help lead this great organization that represents people who have chosen to raise their voice in support of innovation in kidney care and greater care choice. Over the last 19 years that I have been with AAKP, my voice has joined the thousands demanding a change in status quo kidney medicine and increased patient care choice without any barriers to accessing all available treatments. When an individual has kidney disease, their health condition quite often doesn't stop there. Many kidney patients often face a variety of co-related health conditions that they must also manage. According to the National Institutes of Health, it's estimated that more than 1 out of every 7 people with kidney disease has anemia. Anemia is a distressing condition that can dramatically impact an individual's health and quality of life. Based on an independent survey AAKP conducted through its Center for Patient Research and Education, 56% of respondents reported that their anemia affected them both physically and mentally. The effects of anemia were compounded by those individuals who were also on in-center hemodialysis, with 88% reporting that they felt they were unable to work at their full-time or part-time job after a dialysis treatment. But what if there was a new FDA-approved treatment for anemia for adults on hemodialysis? Patients just needed access to it. That is precisely where today's session, Innovation in Research, Advancements in Anemia Management, the VOICE trial, comes in. I am pleased to have with us today, joining remotely from Colorado, Dr. Geoffrey Block, Associate Chief Medical Officer and Senior Vice President of Clinical Research and Medical Affairs for U.S. Renal Care. Dr. Block is leading a clinical trial to assess the safety of a 3 times weekly doses of vadadustat. Because AAKP defines kidney disease as both a healthcare and workforce issue, we have taken a particular and strong interest in this study that addresses the critical issue of anemia and are pleased to be a stakeholder partner in this project. I'd like to ask you to turn your attention to the screen as I turn it over to Dr. Block.
Anna, thank you so very much for that introduction. And I wish I was there in person to see all of you. And I hope that I hope you find this presentation interesting. I've been watching online as the loop sort of reeled over the last 15 or so minutes, and I can't help but be struck by the videos that you all saw, which talked about having a patient voice, and that voice being one to advocate for patient choice, and in fact, really a leader in the demand for innovation in our field. And I'm really pleased to be able to talk about both of those things here over the next 30 minutes or so. Let me just start by saying that, well, Diana is absolutely correct. My sort of day job currently is I'm the Associate Chief Medical Officer. I'm one of the Associate Chief Medical Officers at U.S. Renal Care, and I help oversee our clinical research division. I want to tell all of you, when I define myself, somebody asks me what I do, I'm a kidney doctor. I've been a kidney doctor for the last 27 years. My entire career has been spent in clinical medicine. Everything I've ever done from a research perspective has been done from within the confines of a clinical practice. And while I don't see as many patients as I used to, I still see dialysis patients and I see office patients, and I think it's fundamental to what motivates me every day. So it's really been my privilege over that entire time to have led a large number of clinical trials that help bring medicines, many medicines that we use today, in the dialysis center. One quick note. You'll see that some of my slides have branding on them, and I want to actually thank Akebia Therapeutics. Akebia is the manufacturer of vadadustat, the medicine I want to talk about at some length today, and they've been gracious enough to share with me some of their slides. So without further ado, let me move into the topic that Diana introduced to you with her introduction, and tell you that when we think about anemia, we talk about anemia. First off, to be very clear and level set, anemia is a reduction in the number of red blood cells circulating in the blood. And when you look overall Patients with kidney disease are more than twice as likely to have anemia as somebody without kidney disease. Now, we measure anemia. Hey, wait a minute. There we go. That timer said 20 minutes, and I get 30 minutes. So when we talk about anemia, we measure it when we do blood tests. We measure it with something called hemoglobin in the blood, and hemoglobin is a marker of the number of red blood cells that are circulating. So think about anemia as a reduction in the number of red blood cells, and the blood test that we generally get to assess the status of that is a hemoglobin. So if you use a definition of a hemoglobin less than 13 for a man or less than 12 for a woman, all right, you can see that it's twice as common in people with kidney disease. And as kidney disease progresses, the prevalence, the underlying prevalence of anemia gets more and more common. So that by the time somebody reaches stage 4 CKD with a GFR less than 30, or stage 5 CKD not on dialysis with a GFR less than 15, you can see that far more than half of the patients are anemic. When you actually advance in your kidney disease to requiring renal replacement therapy and you're on dialysis or receiving dialysis, whether it's hemodialysis or peritoneal dialysis, you can see in the bars on the right-hand side of this figure that somewhere between 75 and 92% of dialysis patients are anemic and require intervention with one of two medicines. And it's really overall, if you look at all of the patients right now who have dialysis-dependent CKD, and you use this definition of a hemoglobin of less than 12, about 85% of all dialysis patients are anemic. And I'm going to explain to you why that is. The first part of this presentation is going to be a little bit about the basics, the science behind what causes anemia and why what you're seeing is so prevalent. And the second part of this presentation will be really this innovative approach to try and address this with something new, first new therapy in the last 35 years or so. So as I said, we measure anemia, the degree of anemia, using what's called the hemoglobin, and our sort of range of hemoglobin that we aim for is a hemoglobin of between 10 and 11. And frankly, it's hard to get. And many of you may know, it's hard to achieve a hemoglobin in that narrow range. And despite our therapy, we have roughly about a quarter of patients who have a hemoglobin below the range we're trying to get using our current standard therapy. Now, the two things you'll notice on this slide, the things that we give to our patients, you see one is called ESA, and I'm going to talk about that in a minute. And the other is IV iron, which I'm not going to talk about much today, specifics. But these are the two therapies that we give to try to address the anemia that's common in our patients. And the reason for that, the reason that those are the things you're going to see, those are the things we're going to talk about here in a minute, is because in order to make new red blood cells, and new red blood cells are made in the bone marrow, and in order to make red blood cells, we have an absolute requirement for both erythropoietin, which is shortened many times to the word EPO. It's a little confusing because EPO also stands for the brand name Epogen of one of the medicines that we use. But EPO, erythropoietin, is the actual hormone that the bone marrow needs in order to make new red blood cells. And the second absolute requirement for making new red blood cells is iron. And we can get iron from one of two ways. We can get iron from the food we eat, and we can absorb it through our intestinal tract. Or the most common and most important way we get iron is by reusing the iron that's already circulating within red blood cells. As they age, our body recycles those red blood cells, and it breaks down the hemoglobin and takes back the iron. And that iron is stored in cells until we need it, and we release it into the bloodstream to help get back to the bone marrow. So one of the things that is important, and particularly when we talk about the innovation we're gonna talk about with vadadustat, is that this whole process of absorbing iron and moving it from the intestinal cell into the bloodstream, or moving it from the storage cells into the bloodstream, and getting it to the bone marrow at the right moment when they're making new red blood cells and they have enough of this signal, this takes a very, very coordinated response in order to accomplish. The body does lots and lots of things all in a very coordinated way to make this happen. And one of the things that we'll talk about is you don't just have to have EPO and iron, you have to have it in the right amount, and you have to get it to the bone marrow. And this cartoon is actually what happens inside the bone marrow when you take these stem cells and you give them the right signals at the right time, and they mature into the kinds of cells that can divide over and over and over and over again to make red blood cells. We have millions and millions and millions of red blood cells. And so it takes this constant turnover, right? And this constant signaling. So as you see depicted on this cartoon, you need EPO, but you also need EPO receptor expressed on these cells, all right? And you need iron, and you need it delivered to the bone marrow at the right time for those red cells that are maturing in order to be incorporated into hemoglobin and make it out into the circulation. So why do patients with kidney disease, why do 85% of dialysis patients have anemia? And why do more than half of patients, as they lose kidney function, develop anemia? It's because chronic kidney disease affects every single aspect of what I just described. It disrupts every single aspect of what I described. And this disruption essentially starts, if you think about, I don't have a pointer, but if you look at that little cartoon of a kidney, all right, you can see that it starts with, as you lose kidney function, you get abnormalities in oxygen sensing. And we're going to talk about why the kidney and how the kidney is the organ that senses oxygen and responds, all right? But it starts with impaired oxygen sensing. And as a result, the kidney that's no longer functioning normally doesn't make enough EPO, all right? And so there's not enough EPO getting to the bone marrow at the right time. But it's way more than that, all right? As many of you are probably aware and have talked about in previous sessions, chronic kidney disease is a state of inflammation. It's a state of chronic inflammation. Almost regardless of why someone is losing kidney function, the signals for inflammation are increased in the setting of reduced kidney function, all right? That turns on a series of things. By the way, I'm showing you a lot of science. I don't expect you to remember all the science. What I want you to remember are the general mechanisms behind what we do and why this happens. So inflammation causes the increase of this incredibly important protein called hepcidin. And it turns out, we've just learned in the last 2 decades or so, hepcidin is the factor that regulates iron utilization. So hepcidin is what determines how efficiently you absorb iron. It determines how efficiently you can get that iron out of cells and into the bloodstream in order to get to the bone marrow. And because of inflammation that's happening in kidney disease, hepcidin goes up, all right? And you end up having what we call sequestration of iron. So even if you absorb it or you recycle it, you can't get it into the bloodstream and you can't get it to the bone marrow, all right? And then you combine all of those things with the fact that for many of our dialysis patients in particular, the red cells themselves don't live as long. So there's more of a turnover, there's more of a demand, all right? So the point of this is for you to realize that the dysfunction, the problems that occur in chronic kidney disease affect all of these things, and it affects the coordinated response. In the setting of chronic kidney disease, we can no longer actually accomplish this coordinated response that allows us to effectively make new red blood cells and have it timed sequentially in the right order and things done in order to be effective. One of the things that may surprise you and what we're going to talk about moving forward is this concept of oxygen sensing, all right? And unless those of you who sort of stay with your finger on the pulse of what's happening in this space, you may not be aware that the kidney is the organ that really is responsible for the most part for sensing oxygen, all right, and responding by helping the body make more red blood cells. Okay, so you know the many, many things the kidneys do, right, with regard to maintaining fluid balance and maintaining electrolyte balance and maintaining the toxins that get created through everyday life, all right, and the waste functions of the kidney. But the kidney is also exquisitely important in oxygen sensing and response. And it's the kidney that helps drive the sensing of the reduction in oxygen to make more red blood cells that can then be delivered to tissue. And this is an important concept I want you to remember, that when we're talking about a reduction in oxygen, we're not just talking about how much oxygen is carried in the blood. What we're talking about is not enough oxygen getting to tissues. So the body senses when oxygen delivery is inadequate to meet the demands of those tissues suffer. And the consequences depend on what tissue we're talking about. And as Diana said, we now know that anemia, because it's a reduction in the number of circulating red blood cells, what that means is many parts of the body don't get enough oxygen and the tissues suffer. In the brain, it can cause real problems with how people think and how they function. In the heart, it can cause problems with how people feel. It can cause fatigue. It can cause muscle weakness. Right? It's associated with all kinds of ways that people don't feel well. And importantly, it can cause structural damage to tissues. Right? So the response to oxygen deprivation, or the response to a low oxygen, is incredibly important in terms of maintaining overall health and function. The way the kidney does this, and I'm going to talk a little bit in more detail, the way the kidney does this, all right, in when it senses low oxygen, and I just want to draw your attention to the top half of this figure for a minute, all right, that little normoxia, okay, that means normal amounts of oxygen. When the kidney senses a normal amount of oxygen, the cells in the kidney, which make EPO, are essentially active at a baseline level. And in this particular cartoon, those are shown in this they're called REPC cells, right? And they're shown in this sort of light gray color, yellow gray color, all right? The blue cells in between the kidney tubules are the ones that are sitting there not doing anything, but they can be recruited, all right? They can be recruited to become responsive. And so what happens when the kidney senses a reduction in oxygen delivery, a reduction in the number of red blood cells and a reduction in the number of oxygen, those blue cells become active. And you can see in the bottom half of this, they start making a lot of EPO, all right? And that EPO gets into the bloodstream and it goes to the bone marrow where it does its thing to tell your body to make more blood. Now, how that happens and how quickly that happens is exquisitely important. Next slide. And what I want to show you, I think on this slide, is actually the really of great interest. So we all know, I live in Denver, by the way. I practiced my whole career in Denver. So we all know that when you get off the plane in Denver, you come visit me, and there's less oxygen in the air, the first thing that happens is your body starts compensating, all right? Literally within seconds, your heart rate goes up, your respiratory rate goes up, the pressure inside your lungs goes up a little bit. But what you might not be aware of is literally within minutes, EPO starts going up in your blood, all right? And it takes less than a day, all right, for that EPO increase to start translating into increases in hemoglobin concentration. And so if you ask yourself, how can we do it that quickly? How can the body respond, sense oxygen, and immediately respond within minutes to make more EPO and make more red blood cells? And I'm going to share that with you because understanding how the kidney does that, understanding how the kidney senses oxygen and how it can respond so quickly is the basis for vadadustat, all right? Now, the other thing I want you to notice here is that in a normal response, what happens is very quickly EPO goes up. It goes up just a little bit, and it stays up just for a few days, all right? It doesn't have to go up really high, and it doesn't have to stay up for very long. In just a little bit of time, a little bit increase in EPO is enough to make more red blood cells. Now, I want to contrast that, for those of you who are aware, with the way we use EPO today. And by the way, you'll see the term ESA on my slides. That stands for erythropoietic stimulating agent. That is Epogen or a number of drugs like Epogen. So you can think of them synonymously when I say EPO or ESA, all right? Any of the ways that we deliver this today, where we give people a shot of EPO, right, under their skin, results in the blood levels of EPO going very high and then falling very quickly. And then when you get another shot, they go very high and then they fall again very quickly. And that very sawtooth pattern of EPO does not look like what happens normally under normal circumstances. I want to make sure that everyone hears me. The discovery of EPO and our ability to use EPO to treat anemia truly transformed lives. Okay, this was introduced into clinical practice in 1989, and it was a little bit before my time in practicing, but I can tell you that before 1989, people on dialysis required blood cell transfusions over and over and over and over again, hundreds of them per year, right? After the introduction of EPO into clinical medicine, that disappeared. So these drugs have transformed lives, all right? But they're a shot under the skin. They have to be taken 3 times per week, or sometimes weekly or every other week, maybe as long as once a month, depending on the kind. They have to be refrigerated. And while they have eliminated, essentially, for the most part, the need for transfusions, they have some risks, all right? And we've done a number of studies over the last 25 years or so, 30 years, where we kept trying to use EPO to make blood counts go back to normal, to make hemoglobin go back to normal. And I can tell you what we learned is that's not a good idea, all right? Patients with kidney disease on dialysis do not do well with hemoglobins going back towards the truly normal range. And as a result of those studies that we've learned over the last 35 years, every ESA has what we call a black box warning, which is a warning that is meant to be a red flag, an indicator for patients that these drugs have risk. All ESAs have risk. And on the right-hand side, what you can see is simply a figure from a paper not that long ago showing that the more EPO, in this case, one of the ESAs, the more EPO we use, the greater the risk, all right? And so not only do we know we shouldn't try to normalize hemoglobin, we know that we should try to use the lowest dose possible of EPO to achieve making people better. That the people who get the highest doses of EPO have the worst outcome. So what am I getting to today? Let's talk about this class of medicines called HIF, H-I-F. All right, HIF stands for hypoxia-inducible factor, all right? And the class of medicines that I'm going to talk about are called HIF-PHIs. You don't need to remember that. You can think of them as HIF stabilizers or pH inhibitors, and I want to share with you how they work. The science behind this class of medicines is truly amazing and won the Nobel Prize about 4 years ago. One of the 3 members that you see on this slide was a kidney doctor and was studying a particular kind of kidney disease that led to the discovery of how the kidney senses oxygen. So these HIFs, HIF, these HIFs are what we call master regulators, all right? They are transcription factors that regulate that entire coordinated response to try to make new red blood cells. And more than that, they are master regulators of what those organs need to be prepared for and respond to injury due to not enough oxygen. And I'm not going to go through all these things today, but you can see that EPO production and iron utilization are 2 of the things that these HIF medicines regulate. All right. This is how they work. And I'm going to try to make this sort of, I think, in a way that I think makes it understandable, a complex science understandable. It all starts with this molecule in the middle called HIF alpha, HIF alpha. And that's the thing that is being made all the time by every cell. It's constantly being made. So think of that like an accelerator, like pushing the gas. So every cell is making this all the time. But if you have enough oxygen in your blood, you don't need that to be working all the time. And so we have a break. And that break are those enzymes called PhD enzymes. All right. And so if you have enough oxygen in your blood, you're pushing the accelerator all the time, but you're pushing the brake all the time to the same extent. And so that HIF gets broken down and doesn't do anything. As soon as the kidney senses, the cell senses not enough oxygen, you let off the brake a little bit. That's it, for a short amount of time. And so you're already making the hit, you're already pressing the gas, you let off the brake a little bit, and those regulators can go do their thing. And they can cause a little bit of increase in EPO and a little bit of increase in iron. And as a result, you make more blood cells immediately. This is how the kidney can respond within minutes with EPO and within a day to make more red cells. So this is the mechanism with how they work. And I'm going to just quickly mention this slide. I'm not going to go through this, I assure you. I actually found it to be a beautiful slide, but it's just meant to depict for you that this HIF pathway is the way that we coordinate making new red blood cells across all of those things I said, all right? This HIF regulator is what helps make EPO, and it makes EPO receptor in the bone marrow. It's what helps carry iron in the blood. So you make more of the protein that carries iron. It helps make the proteins that help you absorb iron from your food or from your pills. It helps suppress that hepcidin hormone that I told you is so important in regulating iron utilization. All right. So this HIF pathway is the master regulator of the coordinated response of the kidney to help deal with EPO. One of the most amazing things I think about this whole pathway is that this HIF molecule, this HIF PHI, does that in a way that mimics very closely normal physiologic adaptation. So if you look in the middle at what happens, I told you, when you come to altitude with that cartoon I showed, right, where you get this little tiny increase in EPO for a short period of time. If you look on the left, that's exactly what happens with these HIF PHI medicines. All right, vadadustat being the one I'm going to talk about in the rest of this session. All right, so it's very different than what happens when we inject EPO under the skin. So again, we've been using EPO for the last 35 years or so, and it's been dramatically helpful. But we now have an advancement in both our understanding of the science and something that we can use to take that from the bench to the bedside and treat people with a pill that now mimics normal physiology and how we respond through regulating HIF. Now, one of the most fundamental things that I think that supports the potential benefit of this class of medicines has to do with looking at what happens to dialysis patients today, all right, at altitude. Because as I said, at altitude, you activate this, right? And I just want to share with you some really wonderful work done by the folks at DaVita for the most part, where if you can look at the United States as a map based on elevation above sea level, and when you look at EPO use or iron use or hemoglobin response at altitude, you can see that dialysis patients who live at 4,500 feet or higher are less likely to require EPO. If they do get EPO, they use less of it, which is a good thing. They're less likely to need IV iron, and yet they have higher hemoglobins. So they achieve better hemoglobin results, more red blood cells circulating, but they are less likely to need those medicines that we have to give others to get there. And importantly, you see on the next slide is not only does living at altitude affect, how many people get EPO or what their hemoglobin is. What you see is that dialysis patients at altitude are less likely to be what we call hypo-responsive. And you can think of that as a surrogate for needing really high doses of EPO. All right. So being ESA hypo-responsive is not a good thing for dialysis patients. And so people who live at altitude, dialysis patients who live at altitude, are less likely to be hypo-responsive to ESA. And importantly, they have a 26% improvement in their survival. Okay. One of the most basic things we can really look at. All right. So being at altitude for dialysis patient confers a survival advantage. And many of us believe it's related to this HIF stabilization and what it does for helping protect those organs being ready to respond to the stresses of a low oxygen environment. Talk to you about this medicine. This medicine is called Vafseo or vadadustat. It was approved by the FDA in March of this year for people on dialysis at least 3 months, and it will become introduced into clinical practice in January of 2025. All right. I had the privilege of serving for many years on the executive steering committee for vadadustat for the global trials conducted in the registrational phase. And I was one of the authors on this paper we published a few years ago now in the New England Journal of Medicine about its use. I'll just share with you that Vafseo comes in 2 dose forms. It's a pill. It's taken once a day, and it comes in a strength of either 150 milligrams or 300 milligrams. All right. And one of the really nice parts about using vadadustat is that there's only 4 different doses, essentially, that we used in the clinical trial. The recommended starting dose is 300 milligrams once a day, and you can go down to 150 milligrams, or you can go up to 450 milligrams or as high as 600. But that's it. So really, it's a small number of dose steps, which is actually makes it quite easy for patients to take this pill at home on a regular basis, and for the healthcare team to change the dose when they need to without too much complicated actions required by anyone. I want to share with you the results of the trial, and I'm not going to try to go through all of the scientific basis, but I think that you really need to know what the trial showed. And that the trial design for the biggest trial was very straightforward. About 4,000 patients were randomized 1-to-1 to receive either vadadustat starting at 300 milligrams once a day, or to get EPO. In this case, it was called darbepoetin, but get an EPO, an ESA, and they were followed for the next several years. And the efficacy endpoint was, did they maintain hemoglobin? And the safety endpoint was looking at what we call MACE, which stands for Major Adverse Cardiovascular Events. It's a cardiovascular endpoint. So the primary endpoint was cardiovascular MACE, which entails survival, heart attacks, and strokes. And then there were key secondary endpoints that were all cardiovascular endpoints as well. I'm going to show you the data with these efficacy and safety endpoints. Yeah, I want to show you the efficacy results, right? So this is honestly one of the most straightforward results that you can see, all right? So the bottom line is that these drugs were very effective in maintaining hemoglobin. Remember, we want to try to achieve this in that 10 to 11 range. And so by 6 months, people's hemoglobins were in that range and stayed in that range the entire rest of the time on study. And there was no difference whatsoever, no statistical difference at all, between the people who stayed on their EPO therapy, their ESA therapy, or took vadadustat. So from a clinical efficacy perspective, this medicine works to maintain hemoglobin. And it was called non-inferior to darbepoetin. Now, in terms of safety, this is a really important slide. In terms of safety, I told you that all ESAs have this black box warning, all right? And so this vadadustat study was designed to show that vadadustat was what we call non-inferior to use of an EPO, in this case, darbepoetin. And what I want you to look at is these are the endpoints that I described, the MACE safety endpoint, and then these key secondary safety endpoints. So it's an expanded definition of MACE that includes hospitalization for heart failure or a blood clot. It's cardiovascular MACE, it's cardiovascular survival, and it's all-cause survival. And what's most important is this figure over here on the right. This line here is where the risk of that event, any of those events, is neither increased or decreased. The red line is what the threshold the FDA set for meeting the criteria for non-inferiority. And what you can see is that in every one of these categories, vadadustat performed well. While it was not statistically different than darbepoetin, in each one of these, this risk was lower in the group, numerically lower in the group who took vadadustat as compared to the group who got darbepoetin. Again, so not statistically different, but in the right direction for every single one of these endpoints. And if you look here, if you're looking carefully at this slide, this is the percent of patients in each of these groups who had these events. So 18.2 versus 19.3. And in every one of these, that number is lower in the vadadustat arm than it was in the darbepoetin arm. All right. So this gives us great reassurance that this medicine, vadadustat, is not only effective, it's safe when we compare it to darbepoetin. Now, without going into detail, I realize I'm getting a little short on time. I just want to tell you that while the overall results are what I just showed you, what was interesting is that it looked like in a subgroup analysis that the people who required even higher doses of EPO, who we believe, as I shared with you, are at higher risk, the effect of vadadustat to reduce that risk was even more. Now, again, it's not statistically significant because the sample size was not so big. But I just want you to point out that the farther this dot gets away from this line, the bigger the risk reduction, the bigger the improvement. So there's really suggestion that the people who are requiring the higher doses of ESA might get the most benefit from this oral pill. And then overall, let me just tell you that overall tolerability was essentially identical between these two medicines. Not only were the safety events non-inferior with the trend that I told you, the overall tolerability of this medicine was nearly identical to the patients who received darbepoetin as their EPO. So in the last few slides, let me just talk for a minute about how this is going to be used and what we're doing to move this forward a little bit. First, let me tell you that Vafseo vadadustat is currently approved for use in 36 countries outside of the US. All right. So while it's just going to be starting use in the US next year, it's been used in the EU and the UK and Australia and Japan for years. All right. And there's been no new information after all of those patients have been exposed that suggests any change in the safety profile. Now we know, let me just say, we know, many of us know that if we could align people taking vadadustat with their treatment schedule coming to dialysis, we think this would make it easier for patients and make the administration more consistent, right? And so this has actually been studied by Akebia in one trial where they randomized patients to either take one of two different doses of vadadustat 3 times per week or to continue on their EPO. In this case, it was Mircera. And I'll just tell you, the very high level summary of that result was that taking the medicine 3 times per week was, again, non-inferior, meaning it was equivalent statistically to Mircera in maintaining hemoglobin. And if you look on the right-hand side, there was a strong suggestion, again, of a safety improvement. The study was only 300 patients given vadadustat 3 times per week, so we can't draw too strong a conclusion. But if you look, all of these things are in the right direction. Vadadustat treated patients were less likely to need rescue therapy. They were less likely to need a transfusion. They required fewer dose adjustments, and their risk of having a high hemoglobin was lower. Their survival was better, and they had fewer of those MACE events, all right? And the nice part is all of this was accomplished while exposing patients to about 15% less medicine than is required when we take it daily. And so because of that, I want to end with talking about, because we believe that TIW administration is ultimately going to be a really effective way to deliver this, we have designed a trial that we call VOICE. And I think it's ironic how well it fits with the AAKP messaging that we heard in between. And VOICE stands for the Vafseo Outcomes In-Center Experience. And we're doing this within USRC. I've written the trial along with my colleagues. And I went to the FDA, and we are acting as what's called the sponsor investigator. We have received a approval from the FDA that we can move forward with this study. And what we are going to do is randomize approximately 2,200 patients to either receive vadadustat 3 times per week when they come to dialysis center, in-center dialysis, to receive vadadustat or to continue taking their EPO. And it's really that simple. We're gonna randomize patients 1-to-1 to either vadadustat 3 times per week or EPO 3 times per week. And we're gonna follow and see what happens over the next 18 months. We believe that if we can really confirm the results of the study that I just shared with you, that we can advance the utilization of this medicine for patients across the United States and make it more consistent and more simple for patients to receive this therapy. We're thrilled to have the endorsement of the AAKP. We have an academic steering committee. We have an independent data safety monitoring board, and it's one part of our mission, we believe, at USRC and Satellite Healthcare to really do everything we can to change the lives of our patients. I think that together, doing everything we can to educate patients, to educate physicians, to educate the dialysis organizations, to educate our staff about why we believe this innovative therapy can help change the paradigm that we've been using for the last 35 or so years, we're going to do. We believe the data suggests that daily administration is effective and safe. We believe that data from this VOICE trial will influence and potentially inform a broad adoption of vadadustat throughout the United States, and we are excited to help lead this opportunity. So thank you very much for allowing me the time to talk to you, and I'm happy to take some questions.
Great. Thank you, Dr. Block, for a very great and informative presentation, and we're so pleased that U.S. Renal Care is leading this important study. I'd now like to open it up from questions from our live audience. If you have a question, please raise your hand, and an AAKP team member will bring the microphone over to you. Just to give folks an opportunity to kind of get their thoughts together, I would like to pose a couple questions to start us off. First question, Dr. Block. If proven safe, the dosage approach of this particular anemia treatment would help to reduce the already massive at-home pill burden battles with pharmacy refills and enable a real-time assessment of side effects while also offering an alternative treatment option for anemia. There's many who would disregard these issues as insignificant, but as a nephrologist in the field, what does this mean to patients, and specifically the issue of pill burden, which many doctors believe is a myth?
Oh, I'm so happy you asked that question, honestly, Diana. For those of you who don't know, I've spent most of my career studying what we call bone and mineral metabolism, right? So most of my scientific work has been focused on phosphate and how we can treat phosphate and make it better. And one of the most frustrating things that I see over and over again is the way that people blame patients when then there's some lab value that doesn't go the direction that they want, all right? And Paul knows this. I had the pleasure of serving with Paul recently on a committee looking at this and talking about this. I think that pill burden is an incredibly real issue for our patients. What we expect of our patients is enormous with regard to the lifestyle changes that we want them to do, the restrictions we put on people every single day, the number of pills we tell them, and then frankly, importantly, the number of times people change those pills. Every time somebody draws a blood test, somebody wants to change some pill, right? And I think that doing this study, enabling the transition from a daily oral pill to a 3 times per week pill will absolutely help facilitate this. Now, I think that, frankly, the transition from having to take a shot to taking an oral daily pill is important. And I think our home patients in particular, I think, will benefit from that. But if we can ease that burden, if we can ease that how many pills everyone has to take, with proving that 3 times per week is an effective and safe strategy, I'm delighted to do it.
Thank you. And it looks like we have a question from the audience.
Oh, it is on. Okay. Thanks for your presentation, Dr. Block. I just had a quick question. I noticed that daprodustat is also on the market. I guess considering they're both HIF-PHIs, what's the major difference or differences between vadadustat and daprodustat?
Yeah, thank you. It's a great question. I don't mean to be flippant, but the major difference moving forward is that daprodustat's no longer available. So these drugs, daprodustat works the exact same pathway. They have somewhat different effects on those PHD enzymes, and they're somewhat different in their sort of potency with which they inhibit those enzymes. That's not a practical issue. From a practical issue, the difference was that daprodustat came in many different pill sizes. So 1 milligram, 2 milligram, 4 milligram, 6 milligram, 8 milligram, and the dose strengths that you could use went 1, 2, 4, 6, 8, 12, 16, 24. And so from a practical perspective, taking that pill at home was challenging, particularly when we had to change the dose of that. So it works. Let me just be clear. Daprodustat worked as a medicine, and the data was quite good, but it's no longer available.
Oh, we have a question up in front.
Thank you. Hi, Doctor. Thank you very much. I've enjoyed your presentation. I just have a quick question regarding those patients that do home hemodialysis and home peritoneal dialysis. Have you built them into your study, the research that you're going to be doing? And number one. And number two, if someone is interested in this and feel like, that they would want to participate and try this out, how would they hear about it, or how would they go about being able to engage? Or is it just going to be open to a very limited area within the United States or wherever? Thank you.
Yeah, two really good questions. By the way, I hope I look better for you all than I look when I look at myself on this camera. So the answer to your first question is, our study is honestly only for in-center patients, only in-center hemodialysis patients, because it's important. What we want to really narrow down what we're studying to EPO 3 times per week, vadadustat 3 times per week. So we're not studying home patients in the VOICE trial. Now, with regard to where we are going to conduct the voice trial across the United States. Our organization has about 500 dialysis centers around the United States. We're going to be conducting this study in about 130 of those dialysis centers. So, and that's going to be geographically all over. It's going to include Alaska and Hawaii and California and Texas and Georgia and Ohio and Florida and some parts of New York and New Jersey. And so it's hard for me to tell you, exactly, but I think that it is going to be a wide geographic distribution, and we are educating our docs and staff in all of those facilities to help engage patients in joining us on this trial.
And then to add to Dr. Block, AAKP is involved in the voice trial. So through our Center for Patient Research and Education, we'll be working to co-create some of the patient-facing materials and also conducting a clinical trial awareness campaign. So through AAKP, we can help geo-target where those trial sites are, increase awareness about the trial, and then as the trial progresses, at the milestones that it's appropriate to start releasing some information, we'll be working with Dr. Block and the trial group to bring that to AAKP members and the kidney patient community through our webinars and events in the coming future.
And we're delighted and grateful. Yeah.
Okay, do we have any other questions? No? Okay, great. Well, thank you again, Dr. Block. We appreciate you taking the time to join us, and we look forward to working with you on the voice trial.